This video is about acid-base equilibrium reactions. First, we're going to talk about strong acids and bases. Strong acids and bases are those that completely ionize in solution. They do what we call completely dissociate in solution. They break apart to form ions. They dissociate, they break apart. They break apart completely into ions. So we usually show them, the strong acids and bases, with an arrow going all the way to products. In other words, all the reactants react to form products. All of the acid molecules give up their H plus to the base that's accepting the proton. Complete ionization with the single-headed arrow. That's how we really show that these are strong acids and bases. Strong bases are those with hydroxide in their formula. Those with OH right in their formula. Sodium hydroxide, potassium hydroxide, lithium hydroxide, magnesium hydroxide are just a few examples. The strong acids are actually few and far between. There's just these 6 really strong acids. We usually try to memorize these 6 strong acids and know how they're named. There are tons of acids, but most of them are weak acids. So most of the acids out there in the world, like by numbers of acids, are weak, but there are these 6 important strong acids. They're hydrochloric, hydrobromic, and hydroiodic. So this is hydrogen combined with the halogens, chlorine, bromine, or iodine. Then there's nitric, sulfuric, and perchloric. Okay, I was taught this little mnemonic device to help remember the 6 strong acids. And the device I was taught goes like this. It's this phrase, so I brought, so they're out of order here, but it's so I brought no, clean, and then close. You kind of have to keep clean and close straight because clean's for HCl and close is for HClO4. So it's, so I brought no clean clothes. I'll write it down here. So I brought no clean clothes. Again, the SO is for the sulfuric acid, H2SO4, the I for HI, hydroiodic, the brought, HBr, hydrobromic, the no, HNO3, nitric, the clean, HCl, hydrochloric, and the close, HClO4, perchloric. So if that helps you, I like it. It helps me remember those strong acids. Okay, so weak acids and bases. There's a lot of weak acids out there. So most acids and bases only partially ionize in water. These are considered weak acids. So we use this equilibrium arrow to show that we have a weak acid. Previously when we had, HA plus B and it was a strong acid, if we had the arrow and we had a strong acid, that meant like 100% of these dissociated and made, A minus and HB plus, right? So the arrow for strong acids and bases really means that they 100% go to product. When we draw an equilibrium arrow, it's probably like, 99.9% of our acid just wants to stay HA. How much actually goes to HB plus? Probably like 0.1%. So these really slightly partially ionize in water. And so these are are weak acids and weak bases. And this, we have to use this reversible arrow because we've got partial ionization. It's shown with that double-headed or a reversible arrow. That means that the reaction is reversible and in what we call equilibrium. There's this back and forth. Not only are reactants going to products, but products are going back to reactants at any given time. So these are weak acids and bases. These are really what we call weak electrolytes. Okay, they're not forming tons of ions in solution to strongly conduct electric current. These weakly conduct electric current, and so we call them weak electrolytes. And so we've got a forward reaction, HA plus B goes to A minus and HB plus, but we've also got a reverse reaction where HB plus and A minus reverse to reform HA and B. So the original base has an extra H plus after the reaction. That way it can act as an acid, right? If this original base gets an H plus, then it can act as an acid, right? So the forward reaction really has acid and base. Well, here your HB plus is actually acting as your acid and your A minus is actually acting as your base or your acceptor. So things kind of get reversed, just as you might expect in the reverse reaction. They get all wonky. And the original acid has a lone pair of electrons after the reaction, so it acts as a base, right? Here's our original acid with its lone pair. Here's our original base. So they act the opposite in the reverse reaction. So let's talk about conjugate pairs in reversible reactions. In reversible reactions, each reactant and the product becomes and is called a conjugate pair. So the original base becomes the conjugate acid, and the original acid becomes the conjugate base. So in this reaction, water plus ammonia, NH3, reacts in a reversible reaction to make hydroxide and NH4+. Okay, so what's happening? In order to become NH3, go to NH4+, we need an H+ to go from water to NH3. So water is acting as the acid, NH3 is acting as the base. But in the reverse reaction, NH4+ gives NH+ to OH. So it acts as an acid and OH acts as a base. Okay, so in the forward reaction, water and OH minus, they're an acid and conjugate base pair. They only differ by one proton. NH3 and NH4+ constitute an acid-base pair. So these, conjugate acid-base pairs, in general, they only differ from each other by one H+. That's like the definition of a conjugate acid-base pair. So we had water as the acid and OH minus as the conjugate base of that acid. So that was one acid-base pair. Then we had NH3 acting as a base. It was going to accept a proton. But over on the product side, it's got a proton to give away. On the product side, it's the conjugate acid. So they are a base conjugate acid pair. So base conjugate acid pair with ammonia and ammonium. Water and hydroxide are an acid and conjugate base pair. So let's try some more examples because it can get a little confusing. Here's an example. Identify the Bronsted-Lowry acids and bases and their conjugates in this reaction. So we've got HSO4 minus plus water. So it reacts to form SO4 2 minus sulfate plus H3O plus hydronium. So we've got an H going from HSO4 minus over to the water. That's our H plus that's transferring. So if HSO4 minus is giving up a proton, it's an acid. Water's electrons can accept it. It's a base. Then what's happening in the reverse? Well, H3O plus, the hydronium, can give up a proton. So that can act as an acid. We're going to call that the conjugate acid. That's just what we do on the product side. And then SO4 minus is accepting. That's a base. So that will be the conjugate base. And then they're kind of in pairs. You know, we call HSO4 minus and SO4 2 minus an acid conjugate base pair. And then we call water with H3O plus a base conjugate acid pair. So they're paired up like this, an acid with its conjugate base, a base with its conjugate acid. Let's try some more. Again, this can get confusing, but this is a great spot to hit pause and try these yourself. Did you try them out? See how you could do? I think you should. Hit pause. Okay, if you did and you're ready, let's go. We've got CH3NH2 plus water makes OH minus and CH3 NH3 plus. Okay, so our NH2 had to gain a proton from water. So the proton is traveling from water to the CH3NH2. So water is acting like an acid, giving up a proton. And this guy's accepting the proton, so it's acting as a base. To get back and reverse, we have to give the proton back to remake the water. So here we've got an acid, that's our conjugate acid. Accepting is our base, that's our conjugate base. You know, here is our acid conjugate base pair. They differ by only one proton. Here is our base conjugate acid pair, differ by only one proton. Let's look at the next one. Water plus CH3COOH makes CH3COO minus plus H3O plus. So the H is being given up by the CH3COOH to water. So that's an acid. And water is accepting, so water's a base. Again, we're seeing how amphoteric water can be. Here it's a base, here it's an acid, it'll be whatever you need it to be. One thing I want us to recognize is actually things that end in COOH or CO2H, that's a sign of a weak acid. So that is a weak acid ending on a molecule. So that's definitely a sign like beep, 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 acid, that's COOH. Okay, how do we get back where we came from? Well, the proton will travel from H3O plus back. So H3O plus is acting as an acid, the conjugate acid. The conjugate acid to water is a base here. And here we're accepting, so that's a base. It's the conjugate base of the acid here. So let's do some more conjugate acid base pair practice. It says write the formula for the conjugate acid and conjugate base of the following. And again, they differ by only one H plus. So to make an acid, add an H plus. To add an H plus to water, we'll get H3O plus. Remove an H plus from water to get its conjugate base. If we remove an H plus, we'll have an O with only one H, not two. And instead of being neutral, if we've taken away an H plus, we'll be negative. Really, because neutral and negative makes positive. Or, you know, negative and positive makes neutral, however you want to think of it. This is a great place to pause and try the remaining 3 conjugate acid-base problems yourself. Then I'll explain them. Okay, if you tried these 3, you're probably ready to check your answers. The conjugate acid of NH3 is NH4 plus. Of CO3 2 minus is HCO3 minus. We're just adding an H plus. That kind of neutralizes out one of those negative charges. For H2PO4 minus, we'll have H3PO4, and it'll be neutral, again, because that positive kind of neutralized out that negative charge. Okay, the conjugate base of NH3, we've got to subtract an H plus. We end up with NH2 minus. Of CO3 2 minus, subtract an H. There's no H to get rid of, so we can't do that one. That one can't happen. How about getting rid of an H here? We'll end up with HPO4, and now it's 2 minus. So this concludes our, introduction to acid-base equilibrium reactions.